Now you see my screen.
Yes, perfect, thanks.
Okay, good. So I'm going to talk about the selective near-infrared sensitized solar cell for color neutral and highly transparent photovoltaics. So what is a dye solar cell? So very shortly, a dye solar cell is a photoelectrochemical cell. This is the only technology actually that rely on electrochemical processes. And because of that, it's composed of two electrodes that are separated by an electrolyte containing a redox mediator. So the core or the heart of the technology is the dye. So typically it's ruthenium polypyridine complexes, but there is actually the mainstream on donor pair acceptor organic dyes. I would say the beauty of the technology is that this is a molecular devices, and as such, depending on the dye structure and the modifications that you can make on either the donor or the acceptor unit, you can very finely tune the absorbance of the dye, which gives you the possibility of have the way at least to different coloration of the devices, going from black, red, orange, green, it can be blue, purple, and so on and so on. So that's one advantage of having a molecular devices. The second important thing is that it's a technology that has been developed for more than 30 years, and actually it takes a really good advantage of all the visible range from 400 to 700 nanometers. And the dye solar cell can make this conversion very perfectly with quantum efficiencies very close to 100%. But the thing is that half of the solar radiation is in the near infrared region. And based on the dye solar cell, we estimate that we can still absorb and convert efficiently the range of 700 to 950, 1000 nanometers, so all these points. Of course, the research on prochromatic dyes toward the near infrared is not something which is new. There is many dyes which are panchromatic based on ruthenium polypyridine complexes or based on osmium complexes, which today achieve more than 11% power conversion efficiency. In parallel or by contrast, you can also try not to develop a panchromatic dye, but to develop a selective dye. And developing a selective dye will move your research from typically metal organic complexes to purely organic deep IR structures. For near-infrared selective, there is, I would say, two main family of dyes that have been developed. The first one stems from Arakawa research on the cyanide dyes, so very closely related to what Richard Lund was showing during his presentation. And the group of Arakawa achieved 2.3% PC, however, with a very thick, opaque titanium dioxide electrode of 25 micrometer thickness. So no transmittance at all. Also, let's say 10 years ago, we come up also with squarine dyes, and especially dimer of squarine dyes, which we achieved also on opaque titanium dioxide electrode 1.3% PC. So when talking about semi-transparent to selective near-infrared transparent DSSC, it's also not a new field for the dye solar cell. So there's been more than 10 years research on semi-transparent dye solar cell, which can be either green, blue, orange, red. For instance, the most, I would say, important or the top of the state-of-the-art in semi-transparent dye solar cell stems from the work of Zhang et al. That has been published back in 2014, where they combine two types of dyes, one blue one and one red one, and they come up with semi-transparent devices for which the efficiency was 3.7% and the maximum transmittance 60% around 550 nanometers. Industrialization goes, so Solaronics, Edge Glass, they are promoting semi-transparent modules for BIPV application or urban streets applications. So now, why not moving from semi-transparent to purely transparent DSSC? And this is a topic that we set in my group for now a couple of years ago. I think that we started back in 2014 in collaboration with our colleagues from Torino, and we developed they developed more than 20 dyes for the near-infrared selective devices. And one of the dye is the following. This is the cyanine, the polymethylcyanine dye, which, let's say, the advantage or the beauty of this dye is to bring this S0S1 transition far away from the photopic response of the human eyes. But more importantly, and also very difficult, is to bring the S0SN transitions, so the upper lying transitions, outside the photopic response, because often of the near-infrared dyes, you have a background of absorbance in the visible range, which makes your dye having more or less a strong color in the visible range. Here, the S0SN transition is located at 400 nanometers, so at the region where the human eyes are not sensitive to. So with this dye, so we've made different study. I'm going to show you the photodynamic study in solution of VG20. This is how we coded that dye. By time resolved photoluminescence, the excited state lifetime that we measured is about 400 picoseconds. And by femtosecond transient absorption spectroscopy, we also measured 410 picoseconds, so in the range of 400 picoseconds for the excited state lifetime. By comparison, a ruthenium dye exhibits a couple of nanoseconds, even to more than 10 nanoseconds lifetime. So why the excited state lifetime is so short in cyanine dyes? This is because there is a poor electron delocalization in the excited state, and this is the result from TBDFT calculations showing the frontier orbitals of the HOMO level of the dye and the LUMO level of the dye, and you can see that the HOMO levels are mainly located in the core or in the central unit of the cyanine dye, but at the excited state, main of the spin density remains in the central part. So we do not have a very efficient delocalization of the excitons within the molecule, and this is the reason why that the excited state lifetime is that short. Second important point is the molecular aggregation, because cyanine dyes are prone to aggregates strongly or more strongly in solution. So you can avoid the aggregation in solution by going to very diluted solutions. So typically we work with 100 micromolar dye solution concentration. But when you consider the aesthetic aspect, but not only the aesthetic aspect, also in terms of performances, because the aggregates will quench your excited state, when you deal with the aesthetic aspect, the molecular aggregation is a very important factor, because it can make your molecule and your electrode absorbing in the visible range because of H aggregation. So for instance, this is here a photography showing you a device which has been sensitized using VG20 dye without the aggregating agent. And stepwise, we add in the dye solution the deaggregating agent, and you can see how the color can be turned from a deep green into something which is transparent. Here it's a comparison between the UV-Vis absorption in solution of the dye and the self-assembled monolayer for these electrodes. And you can clearly see that when the dye is self-assembled on the surface of the titanium dioxide, how broad can be the absorbance of your electrode. And all this residual absorbance in the red part, but we do have also residual absorbance in the blue part, make this green coloration. Now, what happens when you add this deaggregating agent, which is also a co-adsorbent, luckily for us? This is the quinodeoxycholic acid. So what happens when you add the quinodeoxycholic acid? You can see that the absorption band of your dye on the surface of titanium becomes narrower. It's not as good as in solution, unfortunately, but it's sufficiently good to make your devices transparent. If you make also this comparison between the chemisorption and the solution, you will find out that the quinodeoxycholic acid with a concentration of 50 millimolar, which goes to the surface on the titanium at this threshold, tends to break this H-type aggregation, less the G-type aggregation. In terms of performances, I'm not going into the details. We've made so many electrodes, so many devices, probably since 2014 on VG20, we make more than thousands of devices to try to modify the additives, the composition of the electrolyte, the solvent, etc., etc. But as I would say, a champion devices, one important parameter is coming to the temperature sensitization. This is something that we published 10 years ago. Decreasing the sensitization temperature allows to increase the power conversion efficiency. This was clearly demonstrated in the case of ruthenium dyes. And here we come up also with a good demonstration that this approach works with cyanide dyes. And as a result, you can get up to 3.1% efficiency when you sensitize down to minus 20 degrees, which takes a sensitization time of a couple of days. This is the IPCE curve. You get a maximum of IPC at 860 nanometer, reaching 60%. And thanks for the low sensitization approach, this is the electron lifetime as a function of photovoltaic that is deduced from IMVS experiments. And it shows that the non-geminate recombination can be decreased by 2 to 3 times just by decreasing the temperature. Aesthetic is an important aspect. This is how it looks like our devices, actually. You can see that this is in our building, and you can see that it still has this yellowish color. The yellowish color stems from the redox couple that is in the electrolyte that is based on iodine iodide. Actually, the AVT is 70% and the color rendering index is 92% when we use this iodine iodide redox couple. But I will come back to other type of electrolytes that can be developed or that are under development in the group. So which steps actually limit the performance of VG20 dyes? We did a quite substantial study by picosecond pump probe transient absorption spectroscopy and also with femtosecond transient absorption spectroscopy to monitor the rate of regeneration and the rate of injection. So VG20 in solution, this is the absorbance change. And when you add cerium 4+, which acts as an oxidant, then you can see the formation of the radical cation of VG20, which absorb in all the visible range. But very luckily for us, it absorbs but 25 times less than VG20. So this is something which you will not see in the devices. With respect to the regeneration, 2 sets of experiments has been performed. The first is including a redox couple in the electrolyte, and then you can measure the regeneration time of the dye with the redox couple. So this is the result with a strike image of the regeneration of the dye. It is here in microseconds. You have the ground state bleaching and you have the transient of the radical cation. And the bleaching of the radical cations is due to the all transfer to the redox mediator, and this bleaches within 2 microseconds, which means that the regeneration, half of the regeneration takes place within 2 microseconds. Now you can make the same experiment, but without the redox couple, and it come up with a new strike image showing a millisecond time scale, not a microsecond, but a millisecond time scale. And this is to probe the geminate recombination, how fast the radical cation will take the electrons from the titanium dioxide. And this reaction is very, very slow. You see a couple of milliseconds, and this is the transient decay. And we have 2 components, one short decay with one short component within 2 milliseconds, and it remains a very, very long component, well above 5 milliseconds. But if you take that ratio, 2 microseconds, 2 milliseconds, so regeneration is 1,000 times faster than the non-geminate the geminate recombination, which means that the regeneration yield is 99.9% at least. So no problem with the regeneration. Now, what about the injection from the excited state? So you can make the same type of experiments using transient absorption spectroscopy, but in this case, in the femtosecond time scale, with injecting titanium dioxide or non-injecting zirconium dioxide, which allows here to probe the injection and here to probe the deactivation path of the dye, either through energy transfer from monomer to aggregates or either just bioluminescence. I'm not going to go into the details of the global fit and all the time constant that has been measured, but the story is the following, or the sum up of the story is the following. The problem with these cyanide dyes is typically that the injection, which takes place within 8 picoseconds, compete with a deactivation process that is the energy transfer from the monomer to the aggregates. And this energy transfer takes place at least 5 times faster than the injection. This is the problem one. Problem two is that injection also compete with the fluorescence of the dye when it's chemisorbed. So fluorescence of the dye when it's chemisorbed takes within 20 picoseconds. So in solution it was 400 picoseconds, but when it's chemisorbed it's only 20 picoseconds, and this time compete already with the injection. And the last point is that the injection from the aggregates unfortunately is slower than the deactivation path. So typically only injection from the monomer takes place, and this is in strong competitions with the energy transfer and the deactivation of the dye. And this is perfectly in line with work from Ziolek in Poland, reporting also the same conclusion with another type of cyanide dyes. So typically, if you consider the different times for the electron transfer or the energy transfer, you come up with an injection yield of only 40%. And why this energy transfer from monomer to aggregates is so competitive is because all the spin density is located in the central part of the dye, and with the aggregation, you aggregate with a spin density, a very important spin density here. And this is the reason why that energy transfer takes place favorably through the aggregates and not the injection.
So Fred, we are going away from time.
Oh yes, this is my last slide. This is coming back to now a colorless electrolyte. A colorless electrolyte is important for the application, and we come up with the sulfide iodide system, which allows to have a fully transparent electrolyte. It has a little cost in terms of efficiencies. We reach 2.9% efficiency, but if you look to the aesthetic, this is perfectly transparent and color neutral, since we reach AVT up to 80% and color rendering index of 96% with an efficiency close to 3%. Then goes to the conclusion, and very sorry for that, goes to the conclusion, we even recently patented a new molecule in collaboration with our colleagues in Nantes and the group of Fabrice Audobel. I'm not going to develop this, but we reach more than 4% efficiency with these aesthetic values. And this is a picture of the final devices, and also very good stability compared to regular polymethyl cyanide dyes. Conclusion and take-home message is that we reach an average PCE. Now we are at 4% efficiency. AVT can be up to 80%, CRI can be up to 96%, which is a very, very good aesthetic values and good efficiencies, I would say. So I took a figure from Richard, but I think that is not up to date now, where we located the state of the art for different organic TPV, inorganic TPV, perovskite TPV, where is the state of the art and where actually the near-infrared dye solar cell standard. I would like to thank all the people working on this, let's say, presentation of the data that is being shown here, and also, of course, for the European Commission granting this impressive project. Thanks for your attention.
Okay, thank you very much, Frédéric. Yes, I think there's Richard. Yes.
So I have a quick question for you. So the voltage of your DSCC cell is around 0.4. How high do you think you can go?
Actually, the voltage is pretty much limited by the redox mediator because we already lost their 500 millivolts. Actually, the best voltage we got was 520 millivolts with another dye.
If you just took out the dye altogether, what kind of voltage could you get? I mean, or if you let's say you use the bigger band gap dye, what with that redox and TiO2, what's the highest voltage you could sort of,
with that redox, I would say.
But a bigger band gap dye.
We in the group we reach up to 1.02 volt.
Okay.
And typically, I would say 800 millivolts is a standard.
Okay, so I think there's a lot of room to move there. That looks very promising. So
this is where the main energy losses are. Is actually in current we're quite good, but voltage we have many energy losses that we need to overcome. We estimate that we can reach 6-7% within 2-3 years, but we need to work on the redox mediator. Michael, yeah?
Yeah, hi. Actually, Richard's question is a very good one. And you may have seen our paper in Nature Communications where we have a 1.25 volt VOC with the M5, MS5, Marcos 300H5 die. So the record has, and the record of DSC is now 15.1%. That's full sun, and ambient light over 40%.